Okay, welcome to week 5. Last week we discussed how to take a class that you had developed and make that class an iterable by adding the iter function that returns an iterable object and then defining the next function that takes an iterable and returns the next value from that iterable and raises an exception if there are no more values able to be returned. In this week, we're going to take a look at what are called sequences. If you enable your class to be a sequence, what that implies is that you can subscript within your class or within an object of your class by using the square bracket notation with an integer offset, an integer index, and you can also obtain sequences, or yes, you can also obtain slices of an object of your class. After we've taken a look at sequences involving indexing and slicing, we'll then take a look at two somewhat more advanced features and one sort of, I'm going to call it a minor feature, but we can argue about that. We're going to look at generators and decorators and something called lambdas. And I'll just introduce what these things are as we go, so I'm not going to pre-discuss what those things are. All right, so the idea of a sequence in Python is not quite as strictly laid out in the Python documentation as the idea of an iterable. But as a general thing, in order for something to be a sequence, you have to be able to ask for the length of the thing, and this involves having a correct definition for the len method within your class, and you have to provide a getItem function for your class, and the getItem function will enable you to use individual integer subscripts between 0 and n-1 if there are n items in your sequence. Also, you'll be able to use slicing, that is the, in square brackets, the start, stop, step notation to get a slice of your sequence. Here, to illustrate, I'm just going to use an ordinary list. A list is a sequence. So let me pull up my shell so that we can try this out. I'm going to create M as a list containing 3, 1, 5, 9, 2, 3, 2. Okay, it doesn't matter that much. And we know that we can say len of M to get the length of M. Now, it turns out that when you execute the len function on an object, what's really happening is that the len method is being invoked on that object. And the list class has this len method defined and returns to us a 7. So object len is internally what's going on when you say len m, calling len as a function. I want to also mention here before we get further that something that supports len is not necessarily a sequence. We know that we can create a set of objects. Here I'm creating S as a set of objects, and the set type does support len. All right, so I can ask for the len of the object S. But S is not a sequence. I can't ask for the sub-0 item within a set. All right, so having len is not enough for a data type to qualify as a sequence. We also need to support the getItem And dunder get item in turn needs to support two different possible argument sets. All right, so here's M again, just as a reminder. If I say M sub 3, which we're used to doing, this will get us the value of the sub 3 item in M, so that's going to be 9. This is equivalent to saying M dot get item, dunder get item, with 3 as the one and only argument to this get item function. Okay? Get item can also be called in another way to implement slicing. That is, here is M once again. If I say M sub 2:5, we know that this will give me a slice back from sub 2 up to but not including sub 5. All right, so I'm going to get... All right, when you ask for n item, M sub 3, you get back n item, in our case an int, from the list M. When you invoke a slice, when you ask for a slice of a list, you get back a list. And if you ask for a slice of a string, you get back a string. And if you ask for a slice of a tuple, you get back a tuple. So when you're asking for a slice of an object, you get back probably a shorter object of the same kind. So a slice of an ND array is an ND array. All right, so I'm going to ask for a slice of M from 2 up to but not including 5, and I'm going to get back the list 592. If I try to do this using get item and just directly putting in the notation 2:5, it turns out that that's not recognized. Okay, I can use the notation 2:5 within square brackets, but that notation 2:5 can't be directly used as an argument to the get item function. So we have to know about something called the slice data type. Slice is a data type, like int and float and list and dict are data types. And the construction function or conversion function for slice is just called slice. If I say s, well, I have a set called s, so let me call this slice1 gets slice 2:5. This creates a slice object for me where the beginning of the slice, when I use the slice, the initial item that I will get back is item sub 2 of the sequence, and I will get everything up to but not including item sub 5 of the sequence. I can now say m.get item, m.dunder get item, using slice1 as my argument. All right, using the slice that I have just defined as my argument, and I get back 592. So in fact, when you say M sub 2:5, that gets treated as M sub slice 2:5, which in turn actually gets executed as m.dunder get item with slice 2:5 as the argument to get item. Okay, so frequently we don't even think about this sort of intermediate data type slice. We just directly use the colon notation. But if we want to see how the internal method is invoked, we have to know that the notation 2:5 actually gets converted into creating a slice object with arguments 2 and 5, and that in turn is what gets passed down to the get item function. there are actually 3 different ways that you can invoke the slice construction function. If you just give one argument, that means that what you're asking for is a slice from 0 up to that argument. If you get 2 arguments, or if you give 2 arguments, as I did in my example here, 2, 5, then that's equivalent to asking for a slice from the first argument up to but not including the second argument. And you can also give a step size as a third argument to your slice. So if I say m dot dunder get item slice 4, this is going to give me back a list of everything up to but not including item sub 4. Let me redisplay m. All right, so I'm going to get sub 0 up to but not including sub 4. And if I say m dot dunder get item, well, as I already did. Well, I did 2, 5. Let me just go ahead and do 1, 3. Whoops. Oh, forgot my, I got my first dunder, but not my second dunder in there in that call. Here we go. Okay, so there we are. And now if I ask for a step size as well, if I say m sub 0 colon 5 colon 2, this means give me from item sub 0 up to but not including item sub 5. All right, 0, 1, 2, 3, 4, 5. So these 5 items here, up to but not including the item sub 5, but only give me every other one. So I'm going to get 3, 5, and 2. And that's equivalent to saying m dot dunder get item slice 0, 5, 2. There we go. Cool. So we need, if we're going to implement our get item method successfully for a class that we define ourselves, we're going to need our get item function to be able to handle either an individual int value, in which case we'll just look up one item from the collection, or to be able to handle a slice object, in which case we will look up and return a slice of our collection. How do we do that? Well, fortunately for us, a data type is simply an object in Python, and we can directly compare the type of some variable, that is the type of the object that the variable refers to specific data types like int, str, float, bool, or slice. So we can detect whether some object refers to a slice by simply asking whether the type of that object is slice. And let me, I have a previously written little piece of code that I'm going to use to demonstrate how this works. Okay, so let me pull this up where we can see it. Oh, no. Wrong one. Where is my, where did it go? Okay, I am mistaken. That's okay. I can simply copy and paste this code into my window so that I can demonstrate it. Let me do that. So I'm going to copy and paste this definition of sayType, the function sayType. Great. All right, so the indentation's all messed up. Let me shove in the correct indentation. Tedious, tedious, tedious. All right. All right. Python should be happy now. There we go. And now if I say type of 5, I get told that's an int. If I say type of hello, well, hello, type of hello is not going to be int. It's not going to be float. It's not going to be slice. So I'm going to get nothing displayed if I ask for the type of hello. You can see I can add additional types to this. Say type of 7/3 is going to be float. Say type of slice is going to be slice. All right. So that's how I can detect in my dunder get item function whether the argument that I've been passed is a slice or not. And so here is how I'm going to implement, as an example, for my tuplist class. Remember, this is our silly example class that is implementing the functionality of list using tuples for implementation. To implement the len function, well, fortunately for me, the internal representation of the values in my tuplist is just a tuple. And so I can simply invoke the len function on the tuple that my tuplist object contains internally. And then for get item, I can simply look at the data type of this index argument that comes in. If the index argument that comes in is of slice type, then to create a slice, I need to create a tuplist object containing that slice of the current tuplist. And to initialize that new tuplist object that I'm going to create and return, I can simply use the slice that I've received as an argument for get item and ask for a slice of the underlying self.vals tuple data member within the current tuplist. All right, so I've been asked for a slice of my tuplist. The result of asking for a slice of a tuplist is going to be a tuplist. And the values in that new tuplist that's being created will be the values in the slice. And my values are contained in this internal tuple called vals. And here I'm just passing the slice index that I've received in get item to select out the slice of the internal tuple that I want to use to initialize my new tuplist object with. All right, so that's the difficult part. Now, the other part is if the index is not a slice, then we're just going to make the assumption that it is an ordinary integer value, and I can simply look up in the internal underscore vals tuple object, I can simply look up that particular item within that tuple object and return that value. Okay, let's take a look at some examples of using this. Now I want to actually execute my tuplist code. Let me locate that so that I have the tuplist defined. Okay, so this code here, this is uploaded to Canvas as one of the where's it hiding? Oh, one of the lecture support files. So if you go into the files area, you'll see that there's a folder called lecture support files, and this file, tuplist version 3, tuplist v3, is in there. This has our new and improved tuplist decoration, tuplist class definition, in which we have the iterable that we defined last week. All right, that's Topless Iter. And here are the len and getItem functions that we have just talked about. All right, so this will create a tupless class for me with the len and getItem members that I need. And I'm just going to execute this thing. There we go. It has some test code in it. But I want to do the test code shown in the notes. You can look at the code file to see the test examples at the bottom of the code file. So I'm going to say TL1 gets a tuplist initialized from 2, 5, 11, 9. All right, I have to initialize my tuplist using an iterable. Here I've chosen to use a tuple 2, 5, 11, 9 as my iterable. And now if I just print TL1, I see that it is a tuplist containing 2, 5, 11, and 9. I can test my length function. Rather than doing all the print stuff shown in slide 10, let me just test it directly. I can test the length of TL1, and I get told it's 4. That's equivalent to saying TL1.len. And I can ask for an item from the tuplist using square brackets with an integer, TL1 sub 3. Is, let's see, well, that had better be the 9 here. So TL1 sub 3 is 9. Remember, this is equivalent to saying TL1 dot dunder get item with just plain 3, the integer 3 as my index. You can also use, and I haven't mentioned this, but you can use negative integer subscripts as well. And your implementation of getItem should make sure that it can handle negative subscripts. Now, my implementation of getItem does handle negative subscripts just fine. TL1 sub minus 2 is the second to last item. The reason for that is that if we look back at the code, let me find that code file. Here's the tuplist v3 code file. Okay, so internally, here's the init function for the tuplist class. Internally, we're using a tuple to contain the data in our tuplist. And consequently, if I just pass an ordinary integer as my index into getItem, that integer just gets passed as an index into the tuple. And because the tuple supports negative subscripts, negative integer subscripts, that means that my getItem function also supports negative integer subscripts. Okay, where's the output? Where's the output? Come back, come back. There it is. All right. So that's individual. We've tested the len, and we've tested individual integer subscripts. Now we want to look at some examples of slices. And just as a reminder, here is TL1 again. Whoops. I need to print TL1. All right, so that's what TL1 contains. And if I ask for a slice from 0 up to but not including 2, item sub 0 up to but not including item sub 2. Now, here I'm passing a slice to TL1, and consequently I'm going to get back a probably shorter tuplist as the result, and I ought to get item sub 0 and item sub 1, but not item sub 2. And indeed, if I print TL2, that's exactly what I got. I got the 2 and the 5, item sub 0 and item sub 1, and that's all. I could have said TL2 gets TL1 dot dunder get item. Whoop, forgot my underscores. And I would have to convert the :2 into a slice from 0 up to, but not including 2. And so that's what's actually going on internally. When I say TL1 sub -2 in square brackets, the :2 notation in square brackets gets turned into a slice, and that slice then gets passed as an argument into the dunder get item function. All right, in this next one here, I'm saying TL3 gets TL1 ::2. Now, what this one means is we'll start from item sub 0, and we'll go up all the way to the end of the top list, but we only want every other value. So I'm going to get the sub 0 item and the sub 2 item, but I'm going by a step of 2, so I don't get the sub 1 and the sub 3 items. And it works. Okay, and you can try out this example for TL4 as well if you'd like. All right, so that's it, gets us to the end of how to make your class into a sequence. If you define both the len function and if you correctly define the dunder get item function to handle both individual integer subscripts and slices, then you can do everything with your class that other kinds of sequences can do. Next, we're going to take a look at what are called generators. So a generator is a function that yields some series of values, one value at a time, rather than returning a single value. What the generator function actually does is to return to you an iterable. You can store a reference to that iterable in a variable, and then you can step through that iterable using next or using a for loop, which of course a for loop just translates into using next repeatedly to get the next value from the generator. Since the object that the generator returns is an iterable, you can actually use that any place that an iterable is able to be used. The primary difference syntactically between an ordinary function and a generator function is that you use the yield statement rather than the return statement to define a generator. So let's take a look at how this goes. Let me get back my code. All right, so here's what we were looking at with the tup list. Here is a really trivial example of a generator called genletters. I'm going to define gen letters of S. S is my argument. I'm going to loop through each of the one-character substrings in S, although I'm going to use the LTR variable to refer to each of those. And I will yield the letter as opposed to returning the letter. Now, if I had used a return statement here and I called genletters, I said something like gen letters of hello. Hello would be passed in as the parameter S. My loop would say for letter in S. When I say return letter, that would terminate the function at that point and pass back the little h, and the function would be over. But rather than return, if I use yield, what I get back is a generator iterable, and you see the description here is generator object genletters. Each time I make use of that iterable that I got back, the code runs until the yield statement is encountered, and at that point the function suspends itself and hands back whatever the function is supposed to yield. When I then ask for the next item from the generator, the function wakes back up and continues through its code, and when yield is encountered again, the function is suspended and another value is yielded. This will make, I think, more sense if we take a look at an example. Now, when I said genletters hello, that did create a generator object for me to access this genletters generator logic. But I did not put that generator, I did not create a variable to refer to that generator, so that variable was created and is immediately lost. Let me create an object, a variable name, G1, to refer to the generator that I get back from genletters. All right, so I'm calling genletters with hello again. I just used Joe on slide 13 because it was shorter. But here in my interactive code, I'm going to create a genletters generator object initialized with S being hello. And if I ask, if I just say to display the kind of thing that G1 is, I see that it is a generator. And consequently, I can use next. If I say next G1, I'm going to get the H. Next G1, I get the little E. Next G1, the first L. Next G1, the second L. And finally, next G1, the O. And if I ask for next G1 one more time, I get my stop iteration, which is what I'm supposed to get as an exception when I have stepped all my way through an iterable. Okay, so that's a kind of stupid example. I could just as well create an ordinary, like use a for loop to step through that string. This time, again, I'm going to use genletter, the same function as before, but let me do something slightly different. I'm going to use that generator now, G2 this time, to control a for loop. And of course, the for loop is automatically going to invoke next over and over until the iterable has been exhausted. All right, so this time G2 is genletters Spider-Man. Okay. And for S in this iterable, this generator G2, print S, and let's have the end be a space instead of a new line, so I get these all out on a single line. So a generator is an iterable. It's an iterable defined by a function that has some logic using a yield statement instead of return. One difference between collections that we can use as iterables, like lists or sets or tuples, or dicts for that matter, we can ask for the .keys or .values or .items, is that a generator can produce an infinite number of values. If you create such a generator, that's fine. You just have to be careful not to use an infinite generator to try to create a collection. So if you have an infinite generator and you say M gets list of infinite gen, let's say, well, that will run until your system runs out of memory and crashes. So don't do that. But here's an illustration. I'm going to define counter as a generator. It will accept one argument, which is the first value that the counter is going to return. By default, 1 is going to be the first value returned, but I can specify a different integer. And now I'm going to set up a loop counter called I, initialized to the first value, And forever, that is while true, I'm going to yield the current value of my loop counter, and then I will add one to the counter. Okay, so again, this function will create a generator object. When I invoke next on the generator object, the logic will start running. That is, I will get set to the first value while true is an infinite loop, except it's only going to execute one time here. So true is true. So we come in here and we say yield, and that's going to be the first value. And when we hit yield, count is going to be suspended until I invoke next on that same generator object again. When I invoke next on the same generator object, the function's going to wake back up. It's going to continue with whoops, that's not very good. I wonder if I can fix this. I think I'm probably doomed. Maybe I can. Oh, did it let me? Oh, I got away with it. Okay, so when the function wakes back up, it adds one to I, discovers that while is still true, and yields the next value and suspends itself. So let me create a generator object for my counter. C1 gets counter. Here I'm passing no argument, so the stupid me. I called the thing count by accident. C1 gets count. All right, so this is a generator, and now I can say next C1. And since I did not give an argument here, the default value is going to be 1. So next C1 is going to be 1. Next C1, again, is going to be 2. I can create another counter object, also using the count generator function. But this time I want to set my initial value to 10. So that next from C10, whoops, is 10. Next from C10 is 11, and so on. And so now I have these two independent counter objects, each of which was created by this one, well, I misnamed it count, but each of which was created by this one counter generator function. And as I said, beware that these things are infinite. So if I now say for k and C10, print k with the line separator being a space. Okay, C10 has been moved up to 12, so this is going to print infinitely many values starting from 12. And I'm going to have to hit Control-C to get that thing to stop. It turns out that in addition to defining a generator function by using a yield statement, any so-called comprehension notation that you put inside ordinary parentheses creates what's called a generator expression. You may recall I said something about, and you may not recall this, so I'll repeat it. You may recall that I said there is no such thing as a tuple comprehension. There are list comprehensions. We can say j for j in range 5, and that does what's called comprehending a list of 5 values, 0 through 4. And there's a set comprehension that looks the same, except I'm using curly braces here. So there's a set of 5 values. Or I can do a dictionary comprehension. Let me map j to, the square root of j for j in range 5. So here is a dict comprehension. All right, but if I try to create a tuple comprehension, I get a generator object. Okay, I don't get a tuple. Now, fortunately for me, I can use the tuple conversion function with any iterable, including a generator, to create a tuple. So I can use the tuple conversion function with this generator object to create a tuple containing the values produced by that generator object. The advantage of a generator as compared with, for example, a list of all of the same values, well, for one thing, as I've just shown you, you can create a generator that produces an infinite series of values, which you can't do in a collection. Another problem with a collection is that a collection, such as a list or a tuple or a set, does actually occupy memory on your system. And so creating a list of, 100 million values just so that you can iterate through that list is very wasteful in terms of memory. If you can produce a generator expression that over time, over some for loop or whatever, produces the same series of values as you had planned to put in the collection, then you can get the same series of values. You caught me. All right. I'm trying to say series. I'm trying not to say sequence. Let me explain why. I want to be clear that a generator or a generator expression is not a sequence. Remember that what a sequence is, here I have, I didn't create M. Let me create M. Okay, I'm going to just copy and paste that stuff there. M gets those values. Okay, a list is a sequence because I can access individual items from it. I can access slices from it. And I can ask its length. If I can do those things, then the object qualifies as a sequence. A generator is not a sequence. If I say C5 gets count 5, remember that count is what I accidentally named my generator function. C5 is now a generator function. I can't use subscripting on a generator. A generator is an iterable, and consequently I can use next to step through the items in the generator. But a generator does not support len or get item. Maybe it supports len. I don't think so. No. All right. So So I've been trying to say that a generator produces a series of values as opposed to a sequence of values, whatever. So the point here is that one of the benefits of a generator is that it can generate an arbitrarily long sequence series of values without causing memory to be allocated for those values. All right. So if I say G1 is x star star 2 for x in range 1020, all right, don't get fooled. It looks like I'm creating a tuple here, but I'm not creating a tuple here. I'm creating a generator expression. So G1 is a generator expression. It's not allocating memory. But I can use functions that take iterables to evaluate all of the item values eventually produced by that generator. Let me be clear that once you have used up a generator, you can't do anything else with it. So if I now ask for the next value from G1, I get stop iteration because you create a generator, You use it once from beginning to end, and then it's it's dead. It's like you've reached the end of an input file. You can't continue reading from the end of an input file, and you can't continue getting values, getting next values out of a used up iterable. All right, so if I let me import NumPy as np. If I say np.random.seed of 0, I'm doing this just so that all of us get the same result. I can now ask for 1,000,000 standard normal values by not allocating them all at once, but instead allocating them one at a time in a generator expression. And because 1,000,000 is a little hard to read, I'm using the underscore trick to let me type a really long number. Let's ask for 1,000,000,000. What the heck? This may take a little while to run. Okay, but I want to be clear. I have not allocated 1,000,000,000 ints. I have merely allocated a generator object that, when I ask for next values, will eventually give me back 1,000,000,000 values. And if I ask for the maximum from G2, I get, after a little bit of thumb twiddling, maybe a lot of thumb twiddling. When I did this with 1,000,000, it only took a couple of seconds. So maybe it's going to take 2,000 seconds now. All right, I give up. Let me do this. Let me just say max of np.random.randn for, and notice that I can type my generator expression right in as an argument to the max function in range. All right, we'll just go for 1,000,000. There we go. Okay. Now, in my course notes, I have the value 4.7166, etc. Here, I'm not getting the same value because we used this generator expression, so I forgot to reset my seed to 0. In any case, you can see what's going on. And here at the bottom of slide 18, I'm doing the same thing with sum. I'm computing the sum of that same initial sequence of 1,000,000 standard normal random values. All right. Whoops. Hey. What's going on? Okay. Okay, so that takes care of generators. Next up, we're going to take a look at what are called decorators. And to talk about decorators, we have to first know a little bit more about functions than we already do. The first thing to be clear about is that what is going on? There. All right, my highlighting was busted. Functions are objects, just like types are objects, and ints and floats and classes are objects. And you can therefore pass a function into some other function as an argument, just like you can pass an integer or a string or whatever. You can also specify a different name for a function just by using assignment of an existing reference to a new reference. So here I'm defining a very simple function, plus of xy, to simply return x plus y. Not exciting at all. Plus of 3, 9 is going to be 12. And I can create a new variable, add, to refer to the same function as plus. And now I can say add minus 3 and 8 and get
5. Okay. In Python, you can do what are called nested function definitions. That is, you can define a function inside of another function definition. Here I have a function b being defined as part of the definition of function a. All right? So when I call a, and I'm passing in these two arguments, 3 and 5, j gets 3, k gets 5. I'm then defining this nested function called b, and I'm calling b with j squared, all right? 3 squared is 9, and k over 2, that's 2.5. And printing out the results of j and k after b returns. Now, b gets called first, of course, so b is receiving the 9 and the 2.5 and prints the 9 and the 2.5. And then I get the 3 and the 5 that came in as part of the parameter values for the a function. Now, I just noticed that there's a typo here. This comma should not exist, actually. So let me give this thing a try. I'm going to copy and paste in this definition of A, which incorporates a definition of B. See if my tabs, yeah, tabs are all messed up. I can go back and patch those up, I believe. All right, so there is my definition of A, which includes a definition of B. And when I call A, passing in 3 and 5, in A, J is 3, K is 5, B is defined and then called with 9 and 5 halves as arguments. So 9 and 5 halves come out first, and then from the final print statement, the second print statement in A, 3 and 5 are displayed. All right? So that's nice, I guess. Defining one function in another function is a feature that not all languages provide. Many do, but C++, for example, would not permit you to do this, to define one function inside of another. Not only can we define one function inside of another, but in fact, a function can return a function as its value. Specifically, return a reference to a function. So here I have this function named rfun, which stands for random function. And when I call this random function, within the random function definition, within the rfun definition, notice that I'm defining 4 nested functions. A, which adds and returns the sum of 2 parameters. S subtracts the second parameter from the first. M multiplies the 2, and X divides the first one by the second one. Here, I'm creating a list of these function references, right? A, S, M, and D are the names of these 4 nested functions, A, S, M, and D, A for add, S for subtract, etc. And because I've stored those things in a list that I can index with a value between 0 and 3, I can look up a random one of those by asking for a random integer less than 4, all right? So randint 4 means give me a random integer value back, 0, 1, 2, or 3, with a uniform probability of those, all right? So when I call rfun, what I'm going to get it back is, with uniform probability, either a reference to A, or a reference to S, or a reference to M, or a reference to D. And here's how some examples of that look. Now let me, in fact, define this. by whoops, rats. I have to turn off my highlighting so I can copy it over. All right, so I'll copy it over here now, and I'll clean up the bogus indentation. Okay, so I clipped a little bit of that spacing out of the video. So now I've got my rfun function defined, and if I want to set my random seed to a specific value so that if you try this, you'll get the same results that I do. I'm going to say f gets a random function. All right, and then I'll run f with 3 and 5 as arguments. Oh, okay, so the random function that I got must have been a. 3 plus 5, 3 added to 5 is 8. And if I call rfun again, and say f gets the result of rfun, and now call r again with 3 and 5. Okay, so apparently I got D, division. So 3 over 5 is 0.6. F equals rfun again. F of 3 and 5. This time I must have gotten S. 3 minus 5 is minus 2. Now, F is going to continue referring to whatever the most recent random function was. If I say f sub 3 comma 5, f sub 10 comma 6, you can see that f continues referring to s now until I change f by saying f gets rfun again. And this time around, apparently I got back an A. In fact, I don't need to use a variable to store the value that I get back from rfun. I can just call rfun. That's going to return a function, and so now I can just use another set of parentheses to directly call that function. And I'm getting 15. I'm somewhat out of alignment here with my live screen versus slide 22 because here I called rfun, which did another random number generation, and that's why I got this 8 back from f that time. But now rfun is apparently returning the m, which is multiplying 3 and 5 to get 15. And each time I call rfun, I get back with uniform probability any one of these 4 possible functions. I got the division back that time. And the multiplication back again. And so on. So you can pass functions in as arguments. You can define functions in a nested way inside of other functions. You can even return functions as values from functions. And finally, we know enough to be able to talk about this thing called a decorator. Okay, so to apply a decorator, you use this notation @ followed by the name of the decorator. The decorator is a function. And you do that in front of the definition of some other function that you want to decorate. Okay, so the decorator is a function, and what it does is to wrap some additional behavior around some other function definition. In particular, if you write this notation at and the name of the decorator followed by the definition of some function, that is treated by the interpreter as defining the function, and then following the definition of the function, modifying the function to be the return value of the decorator applied to the function. All right, so well, that's
Who knows what the heck is going on there? All right, well, let's take a look at what's going on there. Here is an example of a decorator. And what this decorator function does, I guess I shouldn't highlight the entire thing. So Chatty here is a decorator. And Chatty actually takes a function as its argument and returns this thing called Chatty wrap. Now, different people have different naming conventions for these wrapper functions. I like to just call my wrappers, whatever the name of the decorator is with underscore wrap on the end. Okay, so if I call Chatty and I pass in the name of some function, within Chatty, we're going to create an inner nested function called Chatty wrap. And what Chatty wrap is going to do is to first display a message that we're calling a function. Then it is actually going to call the function whose name was passed in as an argument. And after that function has been called, Chatty wrap will use another print statement to say, okay, the function returns. So in other words, instead of just calling the function and having it do whatever it does, the function f, what we're going to do is we're going to make that chatty so that when you call the function after you make it chatty, it says calling a function, then it calls the function, and then it says function returns. Let's see how that works. All right, so chatty is going to be my decorator. And here is the function. Here is a simple example function that I want to decorate. Let me type this stuff in so that we can see what's going on. I'm going to define chatty as my decorator. It's going to receive a function as its argument. Internally within chatty, we're going to define a nested function, chatty wrap, which simply says calling a function and then actually calls the function that was passed in as an argument. After the function has returned, we're going to say print function returns. Okay, and that is what our wrapper does as the last step of chatty itself. As the last step of the decorator itself, we have to return the chatty wrap that we have created as a nested function inside of chatty. All right, so that is going to be my decorator. If I now define an ordinary function, define say howdy, this is a very dull function. All it does is to use print to display howdy on the user screen. There we are. So I can say howdy, and it says howdy, and I can say howdy, and it says howdy. Isn't that cool? So each time I call say howdy, it says howdy, and that's all it does. But now let me use my decorator in a non-decorative form, let's say. So I'm invoking my decorator here in the same way when we talked about sequences that we invoked the .dunder len function and the .dunder get item function. I'm illustrating here internally what decorators are doing. Say howdy is the name of a function. Say howdy is actually, though, just like a variable name, and I can change it to refer to something else. So I'm going to modify say howdy to refer to a chatty say howdy. Okay, so I'm calling the function chatty. I'm passing in say howdy as an argument, the name of the function. in the function chatty, f is say howdy. And so in the function chatty, we're going to set up this nested function called chatty wrap, which says calling a function, then it's going to call say howdy, then it's going to say function returns, and we're going to return that chatty wrap function reference as our result. So when I call chatty with say howdy as an argument, what I actually get back is chatty wrap, which contains a call of that function plus a couple of print statements. And I'm modifying the function name say howdy to refer to the chatty version of say howdy now instead. Name chatty wrap is not defined. What did I do wrong? Chatty warp. Okay, let's try this again. I'll copy and paste that and fix it up. Chatty wrap. And now, unfortunately, I no longer have my original say howdy function. Oh, I do. Cool. Okay, so I do have the say howdy function. I thought I might have to redefine say howdy. So now I'm going to say howdy. Oh, that's right, because this the invocation of chatty itself failed, and so the variable name say howdy didn't get modified. The function name say howdy didn't get modified. Now I'm going to modify it by making say howdy into a chatty version of say howdy. And now when I invoke say howdy, we get the chatty version. We get told calling a function, then the function is called and it displays howdy, and then we get told function returns. And now say howdy is going to be this chatty version of the function. Well, so I applied the decorator function manually this way. I said say howdy gets the chatty version of say howdy. But that is uncool notation, so what you really want to do is to decorate the say howdy definition by saying @chatty and then define say howdy. Now the effect of this code on slide 25, where I have defined my chatty function as a decorator, and I'm now applying the decorator to the say howdy function, the effect of what I'm doing here on slide 25 is exactly the same as what I did here. All right? So putting @chatty in front of the function definition is equivalent to creating the function definition and then saying say howdy gets chatty of say howdy afterward. It's just this syntax, I think you'll agree, is much cooler. All right, so we're going to use this cool decorator notation rather than the clunky assignment notation that we did on slide 24. All right, well let me just create a different function. In fact, let me apply my chatty decorator to say hello, which prints hello, and I claim that that has the effect of defining say hello and afterwards changing say hello to refer to the chatty version of say hello. And let's see whether that is true. And yes, apparently it's true. So because I've decorated say hello with chatty, I get the chatty version of hello. Okay, both of these examples were dumb. I'm just trying to show you the syntax. Here is a much more useful example of a decorator, although still this isn't all that amazing. Instead of just saying calling a function and function returns in my decorator, this time let me define a decorator called trace, and it turns out that a function automatically contains within it its own name. So if I have this function f that I'm tracing, then I can find out what the function's own name is by saying f dot dunder name. And so this way I can do something smarter than just saying calling a function, function returns. I can say calling a specific function and then execute that specific function and then say that that specific function has returned. So here's my trace function. Define trace of some function f. And here's my internal wrapper function. I'm going to say print calling f dunder name. Whoop. And then I'll call that function, and then I can say that dunder name, f dot dunder name, whoops, forgot my double underscore, returns. Rats. I forgot to return trace wrap. So let me do this again. And I have to, when I'm done defining the trace wrap function, I have to return it as the final step in creating my decorator function. And now let me trace say hey, print hey, and now when I call say hey, my trace decorator does something a little more useful than my chatty decorator. My trace decorator tells me what function is about to get called, and then that function does get called, and then it tells me what function returned. So if I have like a nested hierarchy of functions calling functions calling functions, and I decorate all those functions with trace, I'll be able to get a very complete record displayed on my screen of the order in which those functions are being called and the order in which those functions returned. So that's somewhat more useful. These examples that we looked at here are still kind of silly because each of the function definitions that we applied a decorator to, first of all, didn't take any arguments. Okay, the parentheses here are empty, so we're not passing anything in. And likewise, we're not returning any value from this function either. So these are not very sophisticated functions that we are decorating. If we want to be able to decorate a function that takes arguments and or returns a value, there's one more layer of stuff that we need to put into our decorator function definition. When we define our wrapper function, here I'm my decorator that I'm creating is called trace2. And inside that trace2 decorator, when I define my wrapper function, what I need to do is to pass down all of the arguments, both positional arguments and keyword arguments, the function I'm trying to trace accepts. I'll say, okay, I'm calling this function, whatever it is, and then into the function that I'm tracing, I need to pass in all of the positional parameter values followed by all of the keyword parameter names and values. If that function returns a value as a return if that function returns a value as a return value, I want to capture that return value and return that value from the wrapper function. Okay, so it's got a couple more layers of statistical goop on it to be able to handle arguments being passed in and values being returned. Let me just copy and paste this thing, and I'll have to patch up some indentation, so I will do that without your having to observe. Okay, so I have copied and pasted and fixed up the indentation of the trace2 decorator, which is able to pass arguments down to the function that I'm tracing and also return a value back from the function that I'm tracing. I cheated on the indentation here so that I could get this particular line to fit on my screen. Python doesn't dictate how much indentation you have. It just dictates that the amount of indentation you have has to be at least one space and has to be consistent. So I've got just a 2-space indentation here for my trace2 wrapper function code, and then a 4-space indentation for the statements contained within tracewrap2. All right, in any event, now let's apply this trace2 wrapper. I'm going to say let's decorate with trace2 this retcat A, B, C, S equals space. Cat here stands for concatenate, and these parameters here, A, B, and C, are intended to be strings. So what I'm going to return from this thing is A plus B plus, A plus S plus B plus S plus C. In other words, S here is going to be used as the separation when I do the concatenation between string A and string B and string C. The default separation is just going to be 1 space. All right, so I have decorated my retcat function, and if I now say R gets retcat of good by Joe, and I use an underscore as my separator, okay, I get told calling retcat, then retcat gets called, and I get told retcat returns, and what retcat returns is being displayed here. Notice that in addition to giving the name of the function that's being called, I'm also displaying the return value of that function as a string from my decorator wrapper. Okay, and presumably this return of ret also worked, so when I now display the value of the variable R, I have goodbye Joe. And if I say R gets retcat this is test, S gets 4 exclamation marks. All right, so I get this is test with 4 exclamation marks as the separator between those strings. Other uses of decorators allow you to add timing to a function that you want to call and doing much more sophisticated kind of tracing and debugging of things. We're not going to get into decorators deeply. I just wanted to show you what a decorator is and how you can define a decorator and use a decorator, so that, you know, if you find yourself doing this in the future, or if you get asked about decorators in interviews, you will have seen this notation and what's going on with it. The last thing we're going to take a look at here is lambda expressions. A lambda expression is like a very short function definition of an anonymous or unnamed function. And the notation that you use is the keyword lambda followed by a list of one or more variables and a colon, followed by an expression. And that expression is evaluated based on the values of these variables, and the value of that expression becomes the value produced by the lambda. So roughly speaking, saying lambda of some variables and then colon and some expression is equivalent to defining a function that takes some variables as parameters and that uses those variables to compute some result in an expression and then return that expression. The primary difference here is that the function f has the name f, whereas the equivalent lambda has no name. So what in the world good is this? That's a good question. Let us take a look at a couple of very simple examples, and then I'll show you a context in which they're useful. If I say lambda of x squared, that is a legal lambda definition, and I get told that this is a lambda function, but unfortunately, although I have defined this lambda function, the minute I define it, it just vanishes. You know, it's basically the same thing as saying 5. Okay, fine. I said 5. 5 is displayed, but now that 5 is gone. You know, I don't have any way of accessing that 5 anymore other than by typing it over again. Well, so what you do with a lambda is to call it. So let me put my lambda, I'm going to copy and paste here. Let me put my lambda inside a pair of parentheses so that I can then use another pair of parentheses afterwards to provide a value for x in parentheses. All right, so this lambda expression is essentially a function, and I'm passing in a 9. When this lambda is evaluated with x set to 9, what I'm going to get is a result of 81, 9 squared. What? What's wrong? There may be some stray invisible character in here that I can't see from doing the, oh, I misspelled lambda, that's why. No, I was going to blame it on the copy and paste, but it's not the copy and paste, it's the fact that I can't spell. So let's get the B put in there. And now it'll work fine. So now I get 81. So that's an example of a lambda that has one argument. Next, I have an example of a lambda that takes two arguments, that we'll call x and y, and simply computes the sum of x and y. And let me call that lambda with the values 3 and 8. Well, 3 and 9 is just good, so that's going to get me 12. Okay, so those are two very simple lambdas, one which takes one argument, the other which takes two arguments, and of course we can have, you know, basically as many named arguments as we would like. It it turns out you cannot have any kind of statements within a lambda. So you can't say return, you can't evaluate an if, you can't use a loop. All you can have are fairly simple expressions that simply use the arguments that have been provided and perform some computation. Now you can do logical comparisons. You just can't use if else. I can say lambda x x mod 2 equals 0, 5, and that gives me a false. All right, so here I'm here the expression I'm evaluating is a Boolean expression. But the what you can put in a lambda is pretty limited. You're also restricted to one expression. Now the expression can be long, and if you put the expression in parentheses, you can split it across multiple lines, but it's just one expression. Now, so what good are these things? Well, sometimes you will encounter functions that take a function as an argument to modify how the function behaves. And in the case where you have a function that takes a function as an argument, rather than providing a named function, you can pass in a lambda instead. For example, if I create a list of values, 7, 2, 12, 9, 3, 4, 13, forgot my equal sign. We know that we can sort a list. That's, sort is one of the methods that the list data type provides. And by default, I get non-descending order. But it turns out that you can specify a function that will pick out a key by which the value should be sorted. Let me illustrate this by recreating the same list again. All right, so here is my original unsorted list now. If I say m.sort with a key of, and here I can give a function, but since I don't have a function lying around, I can just type a lambda right here. This is a function, it's just an unnamed function. Let's figure out what's happening here. So m contains these values, 7, 2, 12, 9, 3, 4, 13. And as the key by which I do the sorting, I'm going to apply to each one of these values in the list m this lambda. So I'll take the value 7, for example, and I'm going to sort that as though the value is 7 mod 2 is 1. Okay, so I'm going to sort 7 as though 7 is 1. I'm going to sort 2 as though 2 mod 2 is 0. All right, so the 2 should come ahead of the 7 because 7 sorts as 1, 2 sorts as 0. 12 also sorts as 0, 12 mod 2 is 0. 9 mod 2 is 1. 3 mod 2 is 1, 4 mod 2 is 0, 13 mod 2 is 1. So when I actually sort the values in m, applying as my sorting key basically whether the value is even or odd, the result is going to be that all of the even numbers, where the mod is 0, will be sorted ahead of all of the odd numbers. Okay? And so if we were expecting ascending order by value, this looks incorrect. But in fact, what we're expecting is for the even numbers to sort ahead of the odd numbers. All right, so there is one use of a lambda. I don't know if it's that compelling a use, though, because we could have just said define mod 2 of x
to return x mod 2, and then we could have just as well said here's my original list. We could have said m dot sort mod 2, key equals mod 2, and that also works the same way. So there's some people who are really into lambdas, other people who feel that lambdas are just sort of extra notation that you have to learn to prove that you're a Python programmer. I think I'm somewhat in the latter camp. Lambdas in Python are unnecessary in most situations and also not very powerful because of the limitations on how they can be defined. In contrast, in the C language, where you can't have such things as nested function definitions, and where the lambda mechanism is much more powerful, lambdas in C++ are very, very useful and powerful and beneficial. I think they are in Python just because somebody decided to add lambdas to Python. But there is an example of a lambda. I do want to say one last thing about the list sort method. The sort method does what's called a stable sort. That is, notice in the sorted result, the even numbers 2, 12, 4 are in the same order 2, 12, 4 that they were in the original list. And likewise, the odd numbers 7, 9, 3, 13 are in the same order 7, 9, 3, 13 that they were in the original list. So the sorting is done according to the modulus of each value. The zeros come ahead of the ones. But other than putting all of the zeros ahead of all the ones, the actual values, 2, 12, 4, are in the same order in the sorted version that they were in the original version. And likewise for the odd numbers. Alrighty, so what have we done? We have taken a look at, if you have a class, we've taken a look at how you can define your class to be a sequence by giving the len function definition, dunder len, and also the dunder get item function definition, which supports individual integer subscripts as well as slices. Then we took a look at generator functions and generator expressions. Generator functions use yield rather than return. We looked at decorators, and we looked at lambdas. Okay, so those are things that you should know about and be aware of. Some people make a lot of use of decorators and lambdas and generators. Of those, I guess I find generators to be interesting because you can have, infinite generators, and you can avoid allocating memory by using generators. Decorators have their place. I don't think you want to go wild with decorators. Lambdas, I think you can kind of live without. All right, well, that's my final editorial remark. Take care.